So today I am glad to introduce Shiwali Mohan. Shiwali is a senior member of research staff at Xerox PARC, and she received her Bachelor of Engineering in Instrumentation and Control Engineering from Netaji Subha Institute of Technology in Delhi. She began her study on artificial intelligence at the University of Michigan during her master and PhD and in computer science. She has served as a principal investigator for grants from DARPA and the Air Force Office of Scientific Research. And in addition, she has been a key personnel on grants from several government agencies such as Advanced Research Project Agency Energy. She has also led Xerox research on interactive intelligence system, and her current research work on intelligent coaching system for health behavior change is one of the first demonstration of long-term interactive intelligent behavior that was evaluated with the human training in ecological setting. So during her PhD, she led the development of Rosie, a complex agent with end-to-end behavior, including natural language processing, flexible dialogue, computer vision and action control, and interactive learning. This research opened the way to her work on interactive task learning. And with John Laird, she proposed a novel framework that integrates statistical learning with cognitive reasoning for complex intelligent behavior, and won the Blue Sky Award at the AAAI 2018. She's an active leader of the AI community, and she served as the chair of the AAAI Doctoral Consortium for the last 2 years, and co-chaired the annual meeting of Advances in Cognitive Systems community in 2020. I had the great opportunity to meet her during one of those doctoral consortium at AAAI, and she's I'm really like delighted to have her here today. And now I'll give the word to her, and that she will talk about insights from human cognition to design social robots. So thank you once again.
Thank you, Sylvia, and thank you, Talking Robotics, for inviting me. Let me just share. Oh, it's still
start. Yeah. Here we are.
Yes. Okay. Cool. So thank you, Sylvia, for that wonderful introduction, and thank you, Talking Robotics, for inviting me here today. I'm a senior member of research staff at Xerox PARC, and I don't know, it's the new timers wouldn't know, but if there's some old timers in the audience, they would know. It was a lab that led the way to modern HCI and modern, interactive systems. And with my work, I tend to sort of see it as extending this legacy to humans naturally interacting with intelligent machines like robots. Cool. So I'll be talking about Project Eileen today. And this project is currently funded by DARPA under the program called GALA, Grounded Acquisition of Language. And that program is focused on, at least the way PARC has designed this problem, is focused on how can robots learn language so that they can communicate to humans about tasks and learn from them. Cool. So the problem, like what is the problem case that we are working towards? And the problem case is this, that we all expect robots to arrive and take over the world, right? So we want to use robots in a variety of different use cases. We want to deploy them in a variety of different domains. The problem is that once you have to design this robot for each specific use case, right? And that is extremely costly. So if you look at the fetch robot working in a grocery store, every grocery store is designed a little bit differently. It may have different characteristics. So you would have to send a robotics team with that robot and that design, that engineers behaviors that are relevant to that domain. But this is cost prohibitive, right? So the solution that we are working towards is that the AI systems that run these agents, they should be designed so that non-expert humans are able to program the robots through natural interactions, right? So we are working towards a future where humans don't really have to learn robot programming or AI programming, but the AI systems and architectures are designed to interact with humans naturally and then extract information that would be useful for them to operate in their domain, right? So this problem is called interactive task learning. And so the problem sort of began when I was in doing my thesis at University of Michigan, but then in 2017, there was this Armstrongman Forum in Hamburg, Germany. And I think because a lot of your Europeans, you would know what this forum is. At least I didn't know about it. I learned it by participating in the symposium. But it was a lot of fun meeting. It was an actual workshop where we were there for 3 days and we had to work. Like we actually had to write text and we actually had to, create taxonomies and things like that. I had a lot of fun. But this was like interdisciplinary scientists, right? So we had people from machine learning, cognitive architectures, robotics, psychology, computational linguistics, all coming together to then define this problem of interactive task learning. Like, what does it mean for humans, robots, and agents to learn new tasks from each other? And it's a little bit like, it tends to sound like machine learning sometimes, but it's much more than that. Like, you want to learn tasks end to end. Like, you start with an agent knowing nothing about the domain, and you want to slowly build up a full task knowledge. So here's my favorite interactive task learning system. And so I
put it on your head. Ooh, good try. Try again. On your head. Put it on your head. Go ahead. Ooh, good try again. Good try, but you're missing your head. You gotta put it here on your head. You wanna try again? You need help? Help? Okay, I can help.
Cool. So this is my friend's then 1-year-old kid trying to learn something interactively from his nanny. His name is Ishan. And this is what I draw inspiration from where I'm trying to design robotics, like interactive learning robots, right? So it's not just that the nanny is giving him data or labels or supervision. It is very structured. It's back and forth. Like, she asks him to do something, put something on his head. He fails. Then she gives him a little bit more information. She points to his head. She gives him some feedback saying if he's not getting to a state where she's expecting him to. And at some point he realizes that he just can't do it. So he's actively asking for help, right? So there's this nice interactive behavior that that engulfs the learning experience that's underneath it, right? And that's where we want to build towards. So it's not just interaction by itself or learning by itself. It's actually using interactions to really bootstrap your learning and discover structures in the world that you can actually use for task performance, right? So ITL is a new AI problem. It's inspired by human learning behavior, right? And if you can contrast it with classical machine learning, right? So classical machine learning, the framework is it's a batch process. You have data sets and you're trying to infer a model, that can process a data set. And interactive learning, on the other hand, is incremental. You are slowly accumulating experience and you're extracting generalizable pieces of knowledge from that experience, right? Classical machine learning is phased. You first train and then you test. Interactive learning is online. There's no separate training testing phases. You are learning online and your behavior is improving as you make progress. Classical machine learning is passive, right? It's usually a machine learning engineer or an AI engineer that says, okay, now it's the time to learn. Now it's the time to perform. Interactive learning is active by the agent. The agent decides when is the right time to learn. And it's important because the agent can perceive its own failures much more easily than an observer and instructor could. So then letting the agent decide opportunities to learn is central to it. Classical machine learning tends to be big data, but unfortunately humans can't really provide all the data that's needed to learn from those methods. So it creates this constraint that you have to be able to learn from small data, which then motivates relational representations, more reasoning-driven learning as opposed to more statistical learning. And then classical machine learning, usually the data is confounding. You want to get those data sets so that they cover all different kinds of variability in the domain, and that's why you need a whole lot of data to learn from. In interactive learning, we actually assume that the teacher is benevolent, right? Their goal is to help the agent learn, and we start from that assumption, and we really leverage that the teacher is going to provide right answers at the right time. So at PARC, we've been building a neurocognitive interactive task learning system, and I'll just briefly introduce to you what that looks like. Right, so as I said, we are performing, this project is currently funded under DARPA Gala. And DARPA Gala is really focused on what does it mean to learn language, right? What does it mean for humans to learn language? How do children learn language? And what does it mean for AI systems to learn that language? So it asks the central question, where does meaning really come from? And you can, a lot of different fields talk about language acquisition. So it's worthwhile to think about what is it that they're actually doing. So if you look at NLP, so if you look at architectures like BERT or GPT, they are deriving meaning from statistical patterns and word usage, right? They're trying to figure out what are the general patterns under which the specific word is used, and then those patterns are what indicate the meaning of word. And it's really powerful in all types of information, inference tasks. So if you have to search over documents and things like that, but it does not really lend itself to robotics, where the agent must necessarily go from words into its sensing and into its perceptions and into its control systems. Right? So we can't really just use that model as plug and play. It's really designed for informational domains. Then there's the next extension of it. It's called grounded language processing. So a lot of computer vision or NLP scientists will talk about visual question answering. So there's like the image, and that's paired with something that describes it. And then what the meaning you are now learning is like a joint pattern between what you're seeing and what the word is, the context of the word that it's used in. But again, it's like the view is very informational processing, right? You're trying to caption a video, or you are trying to search using language. You're trying to search images using language. Again, this doesn't really lend itself to a robotics domain where the agent actually must act, right? It's not just sensing. You have to act. You have to think about goals and things like that. Right. So the example is something like what would really help sort of situate us in that research is something like this, right? So in panel 1, you have 3 objects, and then say your robot collaborator says move the green sphere onto the red cube. Now, if we only had DLP type techniques, you can identify green sphere and red cube, but what does it mean to move? What does it mean onto? Right? None of this actually exists in this picture. The robot must act to achieve it, right? So the GLP techniques would not really lend themselves to situations like that. So what we did was we went back to cognitive science and linguistics, and that's why I really appreciated what Patricia said, that she's studying, psychology literature and cognitive science literature and trying to understand how would humans solve this problem, and then design computational methods that use that information, leverage that information, and then does things that a human would want to do. And so we went back to psycholinguistics and said, how are humans using language for communication? So there's this hypothesis called the indexical hypothesis, where and the assertion there is that humans use language to focus attention to the right parts of your domain, right parts of your environment, and then putting it together for action, right? So you know what onto means, and you know what that configuration means in the world through previous experiences. You know what the task of moving means, and language comprehension then means you collect all these different components and put them together into a task representation that would allow you to approach the green ball, pick it up, and go down again. So that's what language's purpose is, and that's how we define our language understanding. We have these modules that are computer vision, spatial representation, AI planning, and task. And language processing necessarily connects different elements of language into these different AI components. And that is how we define comprehension. And then language learning would be, how do you map words to these different elements that a robot needs to behave in that environment? All right, so how do we build this system? So building such systems is pretty hard because it requires you to put the computer vision module with AI planning, with dialogue, with natural language processing and things like that. So what we do is we really leverage cognitive architecture research, which is designing and this research has history, a 30-year-old history. So these are a set of computational algorithms, if you will, but they're actually architectures like end-to-end systems that are inspired from human cognition, right? So I usually use the SOAR cognitive architecture, and then some of our work looks at a companion's cognitive architecture, which is designed on the assumption that humans actually don't reason with subsymbolic data, but they actually reason with qualitative representation. So a lot of the work that we do is translating subsymbolic data into qualitative representation that you reason with, and then you compile it back down. So what does our work look like? So our project is called Eileen. It's a neurocognitive architecture. So this is one of the extensions that we are trying to make, that a lot of the cognitive systems, cognitive modeling work operates in the symbolic domain, right? So it doesn't very easily lend itself to a robotics platform where you must process, vision data, you must process control algorithms and all of that, right? So we are building a neurocognitive system for interactive task learning, which encodes part of like the neural network machine learning parts and tries to integrate them with cognitive architectures in a principled fashion so that you can actually do embodied reasoning, you can actually do embodied language understanding, right? So this is our setup, and you're welcome to read the paper. It was published in Advances in Cognitive Systems last year. So the setup is sort of this: you have a trainer, and currently our experiments are reported on an artificial, design trainer, but we are slowly working towards really understanding how humans teach, and then we will, keep changing this trainer to embody or to mimic how humans teach, so that we are able to evaluate our agents. The human trainer is communicating with an agent through a channel, right? The channel has two parts. There's the environmental and situational channel. So this is where the robot is actually able to observe what's going on. And then there's the interaction channel. This is through which the instructor will express an intent, right? So the instructor can say, well, verify that there is a green cylinder on the domain. And this is what the input to our AI agent architecture is. And then the agent processes all of this information and then, comes out with some behavior. So it could point, if it knew what a green was, what a cylinder was, it could point and say that's the green cylinder, right? So how is the agent built? So agent starts with a camera feed, then we have deep vision that's trying to extract and localize different objects. It then also, extracts some properties that are relevant to the domain. Then all of those detections go into a qualitative spatial reasoning module, which is looking at object detections in the metric space and then extracting relational representations out of it. So this would be something like, hey, object B is on the x-axis higher or further away than object A. So these are qualitative representations that are extracted from our detections, and that relational representation, qualitative representation, is then passed on to SOAR, which is a cognitive architecture. And this cognitive architecture has components that we understand of human cognition, right? It has a symbolic working memory, it has long-term memories, semantic and episodic, and things like that. So this, like the history of this architecture is looking at what are the basic components of human cognition and why are humans so intelligent, and then trying to design computational systems that have similar components. And then the expectation is if you design, an AI system that has the same components as human cognition, it would demonstrate same kind of like breadth of intelligence. In the project, we then started using, we are contributing this new module called concept memory, and this is based on analogical reasoning, right? So there's a lot of evidence in cognitive science that humans are not just processing data, but they're actively comparing current situations to what has happened in the past. And it's through doing that analysis, by computing the differences and similarities with previous situations, is how you actually learn. And then the research suggests that, well, if you learn in this way, the learning is much more general, it transfers really well, it's robust to changes, right? So there's a lot of evidence of good kind of reasoning in that, and then we are bringing it into our AI agent design. So this is the inner loop of processing. The agent perceives something, processes it, does analogical reasoning, and at some point it might decide to take an action. So it might say, hey, pick up object A, and then that is compiled through inverse kinematics reasoning back into something that the robot can actually do, right? So now it's doing deep vision and inverse kinematics are all about embodiment reasoning. Qualitative spatial reasoning is what mediates reasoning about embodiment and high-level abstract reasoning. And then, you know, these architectures are operating at a higher abstract level, and our system just compiles information back, you know, up and down through this loop. And in this agent architecture, we then start with, you know, processing language, and that's where a lot of our novelty is. We then have certain language learning modules that are trying to associate words with different parts of the system so that it's reasonable and actually acts. Cool. So how am I doing on time? Okay. Cool. So I just wanted to very quickly go over what this learning looks like. So let me just wait for the video to perform. So here is we are seeing that interaction happening in the robotic domain, and this is where the SOAR reasoning is happening, right? So notice that everything is real time, like it's actually happening online. The other thing about SOAR reasoning architecture is it's what you would call a white box architecture. So it's not just that you put in data and then, you know, an output comes out and everything underneath it is just, you know, sub-symbolic. It's actually some reasoning symbolically, which means that you can actually observe the kinds of processing it's doing. And that is really critical for us, because if you can really observe what's going on, the agent can observe itself, then it can also decide when it fails and when it's the time to learn. But and that's what we really leverage, is it's relying on the agent and its own failures, and that's when it like asks specific questions, right? So let me just show you an example of that. So the instructor said verify that there is a cone, and at this point the agent knows nothing about cones. It knows nothing about what green is or anything like that. Like there's some basic computer vision methods that are pre-compiled and trained that will extract cone-like objects, but the agent really doesn't know that when humans mean cone, they actually are looking for a specific shape, right? It doesn't know that. So then what's going to happen is that it's just going to fail, right? Because it just didn't know anything. So this is very similar to like if you ask a child, like, hey, pick up a green, you know, pick what color is that? And it may just say, well, whatever, like it doesn't know the answer. It will just look at you with confusion. But now that the agent doesn't know, the instructor can try to teach it, right? So if you expose that information that the agent didn't know what to do, the instructor can say that, hey, you know, let me try to tell you, this is a green cone. And then the agent is going to extract information from its vision scene. It's going to, you know, extract some semantic information from these words, and then it's going to try to create, you know, some hypotheses around what green could mean, what cone could mean. And at this point, it will be overtly specific, right? It has only seen an example of a green cone. So for it, like green is a green cone-like object. Cone is also a green cone-like object. So we call these kinds of concepts overtly specific, right? Because you only saw one example, so that's your best case hypothesis. So now, because of that over-specific hypothesis, if someone said a blue cone, this is also going to fail, because that hypothesis about what is a cone and what is green, none of those things actually apply in this situation. And this is where we'll see some sort of white box metacognitive reasoning, right? So it was able to detect that my concept of cone was overly specific, right? So it marked it as over specific visual concept, which means that I now have to put more examples in it to generalize it, so that I'm closer to what humans conceptualize cone as, right? So it identified its gap by itself, and that it knows that, okay, my cone concept was overtly specific, right? So let me try to repair it, let me try to make it a little bit better. So the human didn't really have to say, hey, cone is a shape type it's just detecting all of those things itself, and then it's just going to store the right set of examples and its machine learning in its analogical learning methods, and then at some point it will be successful. So like this is how it would learn. What can also happen, like so you teach a bunch of objects, and what you can now do is try to build upon this knowledge. So you had taught it a lot of objects, and now you can start using that knowledge that it learned and its previous experience, and then build more complex concepts from it, right? So now you can try to teach it right off, left off, and things like that. So so at this point, I'm just, I think, showing that it doesn't know what right off is, so it's going to just fail, right? And now you can try to teach it in that you can say that the red cylinder is to the right of the green cone, and it will just extract the right set of information. And notice that this is the power of representation that we are using, right? The red cylinder, it's using the concept that it had learned for red, for cylinder, for green, for cone, to actually understand which part of the state space that human is talking about and extract the right set of examples. And that's why we don't need a whole 1,000 examples to then generalize this information from. We are using what we had previously learned to really focus on the right elements, right data, sub-data to learn from. And you can similarly, like even if you have distractor objects, blue cone to the right of the red cylinder, even though it may not have seen the scene previously, it knows what blue cone is, it knows what red cylinder is, so it can extract the right data from these two objects. And it knows that this object just exists, but it's not part of where I'm supposed to be learning from. So it's very human-like in its way that it focuses its attention from language understanding and then uses that smaller data set to learn from. So that makes it small data, so it can learn from a few number of examples. And then it's also very interactive, that it can figure out where it's failing and then guide interactions in that way. And then eventually you keep on training it this way, and then it can just even act from those representations. So these are not just abstract representations that it's using to reason with. Let me just so it's actually just planning. So these are, you're seeing planning operators apply, trying to do an action, it can eventually just act out in the environment using the representations that it learned and built up through this incremental interactive experience. Cool. So this is how learning looks like, and what you can do and the way you can evaluate it is just like we came up with these novel ways to evaluate interactive agents. So it's not just test, you train and you test and you're reporting accuracy. You actually are able to understand the profile of learning, right? So the blue bars here are saying how much interaction the agent drives to learn concepts. And here we are learning just noun and adjective like verbs. So you can see that as you have more experience with the domain, you're asking less and less number of questions. You need less and less interactions to learn from. And this tells you that the robot can guide its interactions based on what it really needs to know to perform well in the environment. You also see how general the concepts grow. So at this point, it knows very few concepts. They are mostly over-specific, but with more examples, it's able to generalize them to the right way. And then the specificity is one of the bigger problems with learning from specific to general is that you can just become overtly general. So you can just start thinking everything is right. So here we are saying that it's robust to that. And we did that for visual word learning, spatial word learning, which is right off, left off, on top of, and things like that. And then action word learning, which is actually moving objects to the scene, right? So we demonstrate, so this is something new that we propose, that how do you measure interactive learning in a way that actually makes sense, and it's different from how a typical machine learning thing would be set up. And now we are slowly working towards learning composite objects, right? So we want the agent to be able to build a wall using the blocks that it's seeing in the environment. And we are expecting that all of these components building wall are just taught to it through linguistic interactions. And then we have some evidence that, yeah, the methods that we have built can actually learn the concept of a wall and then use its action planning methods to then plan for building it given its current scene. So Eileen, again, is a neurocognitive architecture. It has these lower level components that are reasoning specifically about the embodiment, the space that the robot is operating in. But all of these components are coupled with these higher decision-making architectures that are following goals of interaction, that are following goals, of tasks and things like that. And then it's finally connected to a concept learning method that's using analogical reasoning, and it's generalizing concepts over relational representations. And all of these systems work together to demonstrate this really complex behavior. And I'm super excited. I feel like by working on this project, we are moving closer and closer to what original goals of AI were, that we want an agent that can just talk to us and demonstrate all these complex intelligent behavior, and we are slowly making progress towards actually building that architecture. So I'm super excited, and I think I'll pause now. There's another part of the work that was focused on, we have until now just focused on what would it mean to design that AI robotics agent, but it's one of the most critical parts of solving the interactive task learning problem is to actually understand how humans would like to teach, right? Humans, it's if you think of machine learning, so if you think of machine learning, and then a lot of the interactive machine learning methods that come out of it, it's easy to believe that the best case is for humans to provide labeled data. Right, but that's not actually true. We found in a study, and again, this is an archive paper, we found that humans actually put a lot of structure when they're trying to teach a robot or trying to teach a robot a robot-like agent, right? They want to break down the task naturally into smaller components. We found that humans were actually breaking it down into first teaching shapes, then teaching relationships and composite objects and things like that. So humans naturally break those tasks down into simpler things that you can actually learn from. We found that humans not only just provided data, not only just provided information to the agent, they actually tried to test it, right? Because that exposes more information about the competency of the agent. And once you know where the agent fails and doesn't fail, you can provide more data. So we saw that behavior naturally arise in human teaching. So we saw that people not only just inform the agent, sometimes they're trying to evaluate, sometimes they're trying the agent to explain itself, right? So it's this dance that has these complex pieces in it. And so if we have to design these naturally interactive task learning agents, we actually have to understand how humans teach and then use that insight to then design interactions that really leverage that structure that humans bring to forth, instead of just thinking of humans as data providing, labeling machines. We actually want to use the structure that humans would bring to teaching. Cool. So I'll just end here in the interest of discussion. So where to from here? We're building these pieces up. The eventual goal is to build towards collaborative learning with embodied intelligent agents, right? We talked about agents learning from humans, but then they're also working on this inverse problem where humans can learn from agents. So imagine you're trying to fix your car and you know nothing about it. So there are these augmented reality classes. It's smart, and then you walk up to your car and it starts teaching you how to actually fix a car. And at PARC, we are starting to again build pieces of what would that look like. And again, these are both problems that really require us to understand how do humans learn and how do humans teach, right? Because once we learn that, we will be able to design the behaviors and the agents in a way that humans can actually work with them. Cool. Thank you for a lot of colleagues from Xerox PARC and University of Michigan, where this research actually began. And then I'll just end here. These are some of the papers that are related to the group. And thank you.
Okay, thank you once again, Shiwali. It was really great. I have tons of questions, but I love when time for questions from everyone. If someone has any question, please feel free to ask. You can raise your hand. You can add it in chat. Let's see. Are there any questions? No? Okay, there is a raised hand. Okay, you can go, Jibko.
Jibko, yeah. Hi, great talk. Really, really interesting integration of symbolic and sub-symbolic components of your architecture. It was really, really impressed. Really cool demo. I wanted to see if you had any more details about sort of how you solve the symbol grounding problem with regards to descriptors of the objects. Is it purely vision-based, or could you perhaps have other methods of the robot identifying whether a particular word the human uses to the object, applies for that object?
Right. So that's a really good question, and we are still exploring what would it mean to really ground the symbols into a computer vision module. So what we now do is we extract like a list of, you could say these are detectors, right? So you have a shape detector, color detector, texture, all of these detectors that are just detecting different groupings in that space. So we have supervised methods, but we also have unsupervised methods that are just clustering similar shaped objects together, similarly similar sized objects together and things like that, right? And they're outputting arbitrary symbols corresponding to those clusters. Now the symbol grounding problem is how we work through the concept memory, which is working with relational representations, and then uses analogical reasoning to figure out, hey, what set of symbols together would map to this object? So the demo that I gave, everything was in one-to-one, right? So green was one shape, color symbol. But you could imagine that there are more complex concepts that one word like a wall would map to not only just symbols that are coming out of objects, but actually their compositions too, right? So that's the analogical learning system, which learns over relational graphical representations, right? So I say these are symbols, but then symbols are also relations between that, right? So if you have robust methods that learn over relational graph-like representations, then you can slowly at some point probabilistically drop out the parts of the graph that were not common in your experience and just really highlight the part of the graph that was common. And that's how we solve the symbol grounding problem. So at some point, you would figure out that balls are of different colors and shapes, but they all have this property that objects are aligned right next to each other, right? So this would just bubble up through analogical reasoning, and that becomes our concept of a wall, and each of those symbols are now like grounded into, because they were generated by the underlying computer vision system, they are directly groundable in that. But cool, thank you for asking that question.
Thanks for answering.
Are there any other?
I have a question. I don't know where is my raised hand.
Okay.
So I have a question regarding the section that you were talking about learning, agents learning from human. So I want to know, so at first, like the description you gave was more like a one-to-one, as you mentioned, like a one color, one shape and stuff. Yeah. And then it's, this is only demonstration-based learning for the agent, or also it will move above like with the communication, like speech, in a sense that, do you have a plan to reach to a level that the agent realizes that what it sees might be different from what the human perceived, like a kind of a mental modeling perspective taking level?
Yes, so our plan is to definitely work towards there. So we already have built, part of the things where if the human said pick up the green cylinder and the robot doesn't know what green is, it can just drive the interaction towards that direction, right? Or if it's conceptual of cone is over specific, it can say, hey, I don't see a cone. Can you tell me what a cone is? Or a more complex reasoning system would do something like, hey, I know all of these objects are cubes. So this other unknown object must be a cone. So let me just ask, is this the object you are referring to? So the representations that we have are conducive to those kinds of reasoning. And in my previous research at University of Michigan, we actually did demonstrate some of that. So I'm very confident that we would be able to move towards more, this mixed initiative learning where through interactions with the human, through what they're saying, the robot is able to figure out what it knows and doesn't know, and then guide the interaction in that direction.
Okay, thank you.
Are there any other questions? Yes, we have a. Okay, so there is a question from Sheng Shen in chat. And the question is, I'm curious about the possibility of learning behavioral concepts about the action of the human and the robot. I'm not sure I understood the question, but if you understood the question, can you please give us some more information? Do you understand? What's the question? Section? I don't know.
I mean, so I could talk about what actions or behaviors for the robot would mean, right? So it's a goal-driven task reasoning component. So it expresses tasks as changes in the qualitative state space that it's extracting from its computer vision data. And what it does is it records all transitions in that state space through examples, right? So if you demonstrated picking up a red object and placing it to the right of the blue cylinder, it will say, okay, first I have to achieve a qualitative state where I'm holding, the human was holding the object. Then the next important state is to reach is where, we are in the right configuration. So it extracts those information through its computer vision and qualitative spatial extraction methods. And it records that in its episodic memory. Like I said, right, that it has its own memory. So it records that. And when you apply analogical reasoning principles on it, you can, with few different move examples, you can actually figure out that it's the object size, shape, and other things don't really matter to the verb definition. Similarly, those other things, the things that where did the object exist in the space doesn't matter. It's actually these configurations, that abstract configurations that matter. And then what we show in the paper is those abstract things we have a multi-level planning architecture. So you can plan first in the abstract space. And once you have the abstract action, those can be through inverse kinematics, used to then do to move the robot. Right, so it sort of compiles back down into it. So the way to think about behavior in this agent is you first abstract away at a high level, then you plan, and then you compile the behavior down into the robot level. But it's basically, is a funnel that goes up and then a funnel that comes down.
Okay, that's cool. Okay, apparently you got the right questions. So there's a thank you for the clear explanation.
Oh, I'm glad. Thank you for asking it.
Okay, are there any other questions? If there are no, I have. Yes, there is. Anna.
Okay, sorry. I really loved your talk. I really like your project, and I think this is fantastic work combining in this hybrid approach, the symbolic and the sub-symbolic. I think it's absolutely great, and this interactive.
Thank you, Anna.
And because I was in the workshop, it's really it has inspired me tremendously. So I was just thinking about an aspect of in your architecture, in your model, what will happen if things go wrong, in the sense that if the agent learns in the wrong way, is there a mechanism to revise?
Right. So so the analogical concept learning component that we have built, it's basically applying some probabilistic reasoning on top of a graphical representation, right? So it measures how many times when you see a concept or human refers to a concept, that edge exists in my representation. And that's what it's learning. So sometimes it could happen that you learn incorrect edges and nodes, right? Just because the environment was set up in a way that you couldn't process it correctly. But our hope is, and we haven't shown it yet, but our hope is with enough examples of right things, like those wrong edges would just fall off the representation, and only the the highly frequent ones, which correspond to actual concepts, were the ones that would be used. So it's very similar to like how it learned an over-specific concept, right? It learned that a cone is actually also green the first time you gave it an example, because that was the only thing it could infer. But then with more examples, it would revise that, hey, the cone is used only in the context of cone-like objects and not green-like objects. So it just learns in that way.
Thank you. Thank you.
Okay.
I really liked it. Thank you.
Thank you so much, Anna. Your feedback really matters.
So thank you all once again. I invite you to keep all the questions that that you have left and share them on our Slack channel. I am now linking here giving you the link to join the channel. We have a dedicated channel for Shiwali, so if you have any other questions, you can ask there. I'll now share again my screen. So I will introduce our yes. We have our next speaker. So I don't know, now you, okay. So our next speaker will be Prashant Madhumal from the AI and Autonomy Lab at the University of Melbourne. And Prashant will talk about causal explanations for reinforcement learning agents. So don't miss it. Please feel free to ask any other questions on Slack. Thanks, Shiwali. Thanks again. And
Thank you for inviting me. I had fun.